Welcome to this explainer on the architecture of molecules. If you think about standard chemical models, like VSEPR theory, they're kind of like a beautiful 3D architectural rendering of a building. It shows you exactly what the structure looks like from the outside. But today, we're going to look at the architect's actual physical blueprint. We are going on a journey from simple two-dimensional shapes to the absolute 3D physical reality of how chemical bonds actually form and literally hold our entire world together. Okay, let's dive into this.
Here is our roadmap for today. We're going to look at the limits of VSEPR theory, then unpack valence bond theory, explore the magic of hybridization, map those shapes directly to orbitals, construct some multiple bonds, and finally wrap up with resonance. Don't worry, we're going to build this logic step by step.
Section 1. The limits of VSEPR theory.
So we all know VSEPR theory is absolutely fantastic for predicting those observable three-dimensional shapes based on the really simple idea of electron pair repulsion. But honestly, it misses the underlying physical why. It gives us the shape, sure, but it doesn't explain the structural mechanics of the electrons themselves. Which brings us to a really provocative question. VSEPR predicts the 3D shapes beautifully, but how do these chemical bonds actually form in physical space? To answer that, we really need to move past simple electron repulsion and look at the physical, quantum mechanical blueprint of the atoms. We need a completely new theory.
Section 2. Valence bond theory explained. Let's talk about overlap.
Valence bond theory is the true foundation of our molecular construction project. It tells us that a covalent bond forms when half-filled atomic orbitals. And remember, those are just the specific regions of space where electrons actually live on two different atoms physically overlap. Imagine two separate, fuzzy clouds of probability moving closer together and finally merging. When they overlap, they yield a shared electron pair that is perfectly situated in that precise physical space between the nuclei. And here is the golden rule you absolutely need to remember. The strength of that chemical bond depends heavily on the extent of this physical overlap. The more extensive the overlap, the stronger the bond physically linking those atoms together.
Now, how do these overlaps actually happen in 3D space? Well, we basically have two primary types of connections. First up are sigma bonds. Think of these as a direct end-to-end overlap, where the electron density is highly concentrated directly on the internuclear axis. That's just a straight imaginary line connecting the two atomic nuclei. These guys are strong, they're direct, and they form the core backbone of molecular structures. Then we have pi bonds. These occur from a side-by-side overlap of orbitals. The electron density here isn't on the axis at all. It's actually concentrated in regions on opposite sides of that central axis, with a node, an area of absolutely zero electron probability, right smack in the middle.
Section 3. The magic of hybridization.
So we've got our standard atomic orbitals, those spherical s orbitals and dumbbell-shaped p orbitals. But sometimes atoms need custom building materials to make the perfect structure. This is where atoms enter the construction phase and start mixing things up. Hybridization is defined as the mathematical process of combining the wave functions for standard atomic orbitals to produce entirely new, differently shaped hybrid orbitals. I actually love to use a mixing paint analogy here because it makes it so concrete. If you mathematically mix one bucket of red s orbital paint with 3 buckets of blue p orbital paint, you don't just get a patchwork of red and blue. No way. You get 4 entirely new buckets of perfectly identical purple sp3 hybrid paint. The atom is literally creating customized, equivalent connections to build stable molecules.
Now, what's really interesting about this slide is how we can visualize this exact process using these energy level diagrams for boron and carbon. Look at how these isolated atomic orbitals on the left completely transform. The atoms are actively redistributing their valence electrons from those isolated s and p orbitals of different energy levels straight into perfectly blended, mixed hybrid orbitals of equal energy on the right. Both boron and carbon are demonstrating sp2 hybridization here, prepping exactly 3 identical hybrid orbitals to form strong, equivalent sigma bonds. It brilliantly illustrates atoms literally optimizing themselves for molecular architecture before they even bond. Section 4. Mapping shapes directly to orbitals.
Let's connect all this abstract quantum math directly back to those observable VSEPR geometries we talked about at the very beginning. And this brilliantly illustrates what is basically the ultimate cheat sheet for molecular geometry. Just count the regions of electron density around your central atom. You got 2 regions, your molecule is perfectly linear, built with 2 sp hybrids. 3 regions, you have a flat trigonal planar shape using sp2.
4 regions gives you that classic 3D tetrahedral shape with sp3. And hey, if your atom is large enough to expand beyond the octet using d orbitals, 5 regions give us a trigonal bipyramidal shape with sp3d, and 6 regions build a complex octahedral structure with sp3d2. The physical geometry perfectly and directly dictates the hybrid building materials required.
So, how do you actually apply this practically? Well, here is a super concrete 3-step guideline you can use to determine the hybridization of absolutely any central atom. Step 1. Determine the standard Lewis structure of the molecule. Easy enough. Step 2. Simply count the regions of electron density around your central atom. But remember, a single bond, a multiple bond, or even a lone pair of electrons, each of those just counts as one single region. Step 3. Take that number and assign the corresponding hybrid orbital set from the cheat sheet we just looked at. 3 simple steps and boom, you've unlocked the atom's structural blueprint.
Section 5. Building double and triple bonds.
Okay, we've laid the foundation with standard single bonds, but let's move up to the skyscraper level of chemistry, right? How do atoms build multiple connections when a single pair of electrons just isn't enough to achieve stability? Let's take a look at acetylene, a molecule that features a super rigid triple bond between its 2 central carbon atoms. The core of this connection is a single, incredibly strong sp hybridized sigma bond centered perfectly on the axis between the carbons. But to build a triple bond, we need more. The carbons use their remaining unhybridized p orbitals to form 2 completely separate pi bonds. These pi bonds overlap side by side, perfectly perpendicular to each other. One overlaps above and below the central axis, and the other overlaps directly beside it. The result? A remarkably strong, multi-layered structural connection encompassing that core sigma bond.
But here's the catch. This structural complexity comes with severe consequences for how the molecule can physically move. Sigma bonds, those single end-to-end connections, they allow for completely free rotation around the internuclear axis. Think of sitting in a swivel chair. You can spin around the center post all day long without breaking it. But pi bonds, because of their side-by-side overlap, they lock the molecular structure rigidly in place. It's literally like taking that same swivel chair and nailing the armrest directly to your desk. If you try to rotate a multiple bond, you drastically decrease that crucial side-by-side orbital overlap, effectively snapping and breaking the pi bond entirely. So molecules with multiple bonds essentially trade rotational flexibility for extreme strength and planar rigidity.
Section 6. Resonance and electron delocalization. Up until now, we've basically been building solid, static structures. But as you know, chemistry is rarely static. What happens when multiple valid structural arrangements exist for just a single molecule? This dynamic reality is beautifully represented by benzene, which is a ring of 6 carbon atoms. If we draw it out on paper, we can draw 2 completely valid resonance forms, with alternating double and single bonds. But the actual physical reality is so much more fascinating. Benzene uses sp2 hybridization to form its flat hexagonal ring foundation out of sigma bonds. However, the remaining unhybridized pi electrons don't just sit in rigid individual double bonds like we might expect them to. Instead, they form a massive delocalized cloud. Those pi electrons are shared equally throughout the entire ring structure, creating a dynamic resonance hybrid that is incredibly stable. Valence bond theory gives us the local foundation for sure, but resonance shows us the whole system in action.
Which leaves us with a final, rather provocative thought to summarize our entire journey today. If valence bond theory maps these localized connections and hybridizations so perfectly, what truly happens mathematically when structures become just too complex and those electrons completely refuse to be tied down to just one local bond? Well, answering that requires stepping beyond valence bond theory and into an entirely new framework known as molecular orbital theory to really understand electrons that roam globally across an entire molecule. But we're going to have to save that fascinating mystery for our next explainer. Keep questioning the blueprint, and thanks for learning with me today.